In the previous video, we talked about the center of mass of a system of n massive point particles. In the real world, and especially in this course, we will have systems like rods, like sheets or solid objects. These things apparently are not just a collection of point particles, but they are some continuous system, right? The question is, how do we find their center of mass? Now, whenever you have a discrete formula like the one you had for center of mass for continuous systems, here's typically what you do. So suppose you have, like right here, you have a solid object like perhaps a stone, right? What you do is you break up this object into small differential elements. You can think of those differential elements as being so small that they are almost like a point, okay? This is just a rough way of thinking about it. So in this case, suppose we break it up into small cubes. Let's say the mass of each cube is dm, and this dm element is located at position vector r. We previously had this expression for RCOM, right? We had RCOM, this position vector of center of mass was 1 by total mass into integration of mi ri. In this case, if we think of this dm as those point-like differential elements, what we do is we want to add up these elements multiplied by the position vectors for all such elements along this object, right? We'll add up dm's we'll add up all the differential elements dm that make up this object. In doing so, we will have to run, instead of a sum, we'll have to run an integration because this is a continuous system. So look at how this formula translates. We have RCOM equal to 1 by integration of dm. So the integration of dm just gives you the total mass times dmr, and the integral is over this whole volume v, okay? The integral is over the whole volume. So now that we have a formula, we could see if we can apply this to a simple system. So one example that we are going to do is we want to find the center of mass of a uniform rod of mass m and length l. Suppose we have this orange rod here. It's a uniform rod. What that means is that the mass is uniformly distributed all over the rod. You know, it's just a well designed, like, straight rod. It's not like it's got no kinks. It's not heavy at one end and light at another or anything like that. For our convenience, we've selected a coordinate system in the following way. So if it's a rod of length L, we select an x-axis. We place one end of the rod at x equal to 0, and then the other end should be at x equal to L because it's a rod of length L. Where do you expect the center of mass of such a rod to be? We know from experience that the center of gravity, at least, is exactly at the middle, right? If we place this rod on a pivot and we place the pivot exactly at the center, then this rod balances, right? And we know that for uniform gravitational fields, the center of mass and center of gravity is at the same spot. Anyway, so our expectation is that the center of mass of the rod should be at x equal to L by 2, right? In this chosen coordinate system, the center of the rod is at x equal to L by 2, so that's where we expect it to be. So whatever calculations we do from here on forth, we expect that the final result for RCOM should be L by 2 I hat, right? If we write this as a vector, it's just L by 2 I hat. Let's see if this plays out. So given this rod of length L, how do we attempt to find its center of mass? First, what we want to do is we want to, instead of talking about the mass of the rod, let's talk about the linear density. Of course, you're probably familiar with using density in volume three-dimensional cases where you say density is mass by volume, but of course a rod like this doesn't really have volume. It's a one-dimensional object. It's only got length. It's It doesn't have any width or height, okay? It's just a one-dimensional object, but it does have mass. In which case, we can define a linear mass density. And then if you take some length of the rod, let's say you take some portion of the rod of length A, how much mass will that have? That will have a mass of m prime equal to lambda A, right? In particular, if you take the whole rod, then it will have a mass of lambda into L, which is m. So that's what it is. It's a linear mass density because it's uniformly massive, right? This lambda would be a constant. This is the constant mass per unit length for the uniform rod. Okay, so now that we have this formula, let's number this one. In step 2, what we do is, as we said, in the continuous case, you want to break up this continuous system into small elements. Let's take a small element of mass dm, which lies on the rod between x and x plus dx. That is, it's got a differential width, a small width of dx. Okay, and using the linear density formula, from which was 1, we have dm, the mass of this small element, is the density times the length of this small element. So we have dm equal to lambda dx. So dm is a small element at coordinate x, and it's got mass dm equal to lambda dx. Good. Next, we want to convert this expression into an integral form. So we convert this to work with small elements dm, and this is what it looks like. Because we only have a one-dimensional object and we are considering the change in x only, so our RCOM would be written like, so in place of mi we take dm, in place of ri we take x, which is the position coordinate of this element dm, right? So that makes sense. This has translated, miri has translated to dmx, and we need to run an integration. What are the limits of integration? We want to run the integration for all such elements di throughout the rod. So we want to integrate from x equal to 0 to x equal to L. And finally, we want to divide by the total mass of the rod, and that will give us the position coordinate of the center of mass. So in the next step, we can write, because we had dm and dm was lambda dx, we can write RCOM equal to 1 by m lambda dx into x. And of course, because this is a uniform rod, we can pull this lambda out of the integral and we can evaluate this integral. It's a very simple one. It's x dx. The integration of x dx is just x squared by 2. So let me work this integration out for you. What we've done is we've pulled out lambda from the integration. Lambda, as we said, was a constant. We have lambda by m, and we have the integration of x is x squared by 2. We have to evaluate this over the interval L by 2, sorry, L and 0, which gives me lambda by m. So first we put in x equal to L, which gives me L squared by 2, and then we put in x equal to 0, so we have to subtract that, and we get lambda by m L squared by 2. But then we did have lambda in terms of m and L, right? We had, in one we had lambda equal to m by L, the linear mass density, which if we plug in here, we have RCOM equal to L by 2. And of course, if you like, you can write that as a vector, right? RCOM as a vector is just L by 2 I hat. This was just the x coordinates, for example. So you found the x coordinate, and as a vector you can write it like this. So just as expected, we found that the position of the center of mass is somewhere exactly in the middle between x equal to 0 and x equal to L, as expected. Now we've done actually a very simple problem. We've just found the center of mass for a uniform rod. You can imagine that these problems keep getting harder and harder if your rod is non-uniform, if you have a very strange shape for which you want to find the center of mass. here's one trick we can use. Suppose we have an extended body made up of a number of continuous systems. Here's one example. For example, suppose you have two massive rods of length L, right? You've joined these two rods together to create such an extended system, right? This is also a continuous system, but you can think of it as being made up of two simple continuous systems. This is an extended body like this, right? The question is, what's the center of mass of this configuration? Your knee-jerk reaction might be to want to integrate this expression, for elements dm along this whole rod. Obviously that would not be such a straightforward thing to do, and you can actually avoid doing this. First of all, let's ask ourselves, where do we think the center of mass should be? From our experience so far, we understand that the center of mass is nearer to wherever there is more mass, right? So we see that for this object, masses are more concentrated here. So we kind of expect that the center of mass of this system might be, somewhere here, right? It would be nearer to wherever the mass is more concentrated. If you remember, when we studied the center of mass of two point particles, we saw that the center of mass is nearer to the heavier particle, right? So how do we do this? We said that we don't always have to integrate. So the trick here is that first you want to replace each of the components that make up this extended system. So these two continuous rods, right? You want to replace them by a point particle that has the mass of this component, but that point particle that replaces it should lie at the center of mass of this component. So we know that the rod on the x-axis has a center of mass here, and we know that the rod along the y-axis has a center of mass here. Let's suppose that these two rods both have mass m. So to replace them, we put one particle of mass m at x equal to L by 2. Another particle of mass m lies at y equal to L by 2 that replaces this rod. So what should we do next? Obviously, we find the center of mass for these 2 points which have replaced this. And in doing so, we have cleverly avoided integration by breaking it up into components and finding center of mass, and then finding the center of mass for those points, right? We should be able to find the center of mass of this whole system. And if we do this calculation, we have RCOM equal to 1 by, just applying the formula for the center of mass of a system of point particles, we have 1 by 2m here, m L by 2 I hat, which is, well, L by 2 I hat is of course this vector, and L by 2 j hat is this vector, and ultimately we have L by 4 I hat plus L by 4 j hat as the center of mass, which you notice is very close to this corner. This is where more masses are, so we found a result that we very much expected.